And we're back and better than ever still in 19-1 where we're dealing with acids and bases, their definitions. In the last podcast we took a look at conjugate acid-base pairs where the difference between a conjugate acid-base pair is the hydrogen ion. The acid has the extra hydrogen, the base, and it's ready to donate that. The base is one less hydrogen ion and positive charge and it's ready to accept it. Now you did notice that there are a lot of substances that behave both as acids and bases. They don't behave the same necessarily in the same reaction, the same molecule, but the compound itself can act as either an acid or a base. That's exactly what an amphoteric substance is. It's a substance that can act as either an acid or a base, depending on the situation. It can act as an acid or a base. So let's go ahead and take a look at that in this table over to the right. I'm going to scroll up here. On the right, we're going to have the compounds acting as acids. And on the left they'll be acting as acids. On the right here they're going to be acting as bases. Okay, so we'll try to identify the various conjugate pairs. Now, if water is behaving as an acid, it's going to have to lose the hydrogen ion. If it loses a hydrogen ion, it's just going to be down to one oxygen, one hydrogen. In addition, it's lost a positive. When it was neutral and lost a positive, it now overall has a negative charge. Alright. On the other hand, in the next example here, if water behaves as a base, it's going to have to accept the hydrogen. When it accepts the hydrogen, it will now have three of them, and it brings the positive charge with it. So if it was neutral, it is now positive overall. And there's our hydronium ion again. So that's why they're called conjugate pairs, because they always are formed when the substance behaves in a particular way. When water behaves as an acid, it always forms hydroxide. When water behaves as a base, it always forms hydronium. Now ammonia is also an amphoteric substance. If ammonia is behaving as an acid, it's going to lose that hydrogen ion. So now it's going to be down to only two of them. Because it's lost a positive charge, it was neutral, it is now negative charge overall. NH2 negative. I believe it's called the amide ion. Don't quote me on that, but I believe that's what that's called. However, if the ammonia is behaving as a base, it's going to have to accept the hydrogen ion. If it accepts the hydrogen ion, it will now have four of them. It also brings that positive charge with it, so it'll be NH4 plus. Alright. Go ahead and work your way through the rest of the table here. You can pause the podcast, and then when you're done, go ahead and start us back up, and we'll see how you did. Alright, so let's take a look at how you did. Go ahead and scrolling down here. If H3PO4 is the acid, when it loses one hydrogen, it'll be down to only two hydrogens. So it'll be H2PO4, and now it has a negative charge because it's lost a positive. If that same H2PO4 now behaves as an acid, it will have to lose a hydrogen. Now you're down to only one of them. You were at a 1 minus. When you lose a positive, you're down to a 2 minus. And now if that HPO4 2 minus behaves as an acid, as it does in the next step, you've lost all of your hydrogens, you're down to none. You were at a 2 minus, you're now down to a 3 minus when you lose one additional positive charge. Alright. Let's try another molecule. If you deal with the bisulfate ion, HSO4 minus, if it acts as an acid, you're not going to have any hydrogens left. It's just going to be SO4 2 minus. It's donated the hydrogen, so you have none left. It was a 1 minus, you're down to a 2 minus. However, if that bisulfate ion behaves as a base, it's going to take on another hydrogen, so now you're up to two of them. You were at a 1 minus, but when you add the positive, they cancel, so now it's no charge, it's neutral. Carbonic acid, H2CO3, when it loses a hydrogen, you're down to 1. So it's HCO3. It was neutral, you're down to a -1 charge. You've lost a positive. The CO3 in the next one down below, this should be a 2 minus charge. If it's behaving as a base, it's going to take on a hydrogen, so now it's HCO3. It was a 2 minus. When you add a positive, it goes up to a 1 minus. All right. And these last two, when acetic acid behaves as an acid, you're going to lose that one hydrogen, so now you're down to C2H3O2. It was neutral, you're now down to a 1 minus charge. When the fluoride ion takes on a hydrogen, becomes HF. It was a negative charge. You've added a positive. It cancels out. It is now a neutral molecule overall. All right, so that's a good look at conjugate acid-base pairs. You will have some questions on there on the test and on the quiz, where if I give you a compound or give you a molecule and tell you that it's behaving as an acid or a base, you should be able to tell me its conjugate pair. All right. Now, finally, and very quickly, because this definition is not one that we typically use in inorganic chemistry. This is something that's typically used in organic chemistry. You have what are called Lewis acids and bases. Lewis acids and bases deal with electrons, and the movement of the particles are actually the opposite of the Bronsted-Lowry. The Bronsted-Lowry acid is going to donate. The Lewis acid is going to accept. But in this case, you're not accepting hydrogen, you're accepting electrons, where the Lewis base is going to donate electrons. All right, so let me switch this color. If we take a look at, let's say, let's go back to our ammonium example. If you have ammonia reacting with hydrogen chloride. Originally, we called this in a Bronsted-Lowry acid-base reaction because this donates the hydrogen. All right, and because this donates the hydrogen, you would say that this is behaving as the acid, and because this is accepting, we call this the base. However, what actually happens, this has a lone pair of electrons, and this actually donates the electrons to the hydrogen as it comes over. The hydrogen is going to accept the electrons, and so therefore that's where the donation and the accepting come along. It's still the exact same reaction. We've just defined it in a slightly different way. Now, once again, you might say, well, what's the point of that? As it turns out, there's going to be a lot of Lewis acid-base reactions that do not involve a transfer of hydrogen. It simply involves a transfer of electrons. And so when you get to organic chemistry and you start moving electrons around, it becomes very, very important. All right. Here's another example that does not necessarily deal with the transfer of electrons. If you deal with ammonia that has a lone pair, and a compound called boron trifluoride, looks like that. What's going to happen when you add these two compounds? This is going to donate the electrons to this molecule, and it's going to form a bond. Not that that's critical to understand at this point, but what you end up with is a molecule that looks like this. Because this did the donating, it is still the base. Because this molecule did the accepting, we still call that an acid. So, taking a look at the definitions one last time. The Arrhenius definition says that acids will produce hydrogens, where the Bronsted-Lowry say that it will donate a hydrogen, where Lewis says that it's going to accept an electron. Arrhenius bases produce hydroxides, Bronsted-Lowrys accept hydrogens, Lewis bases donate electrons. They're simply broader definitions as you move in this particular direction. Alright? Every Arrhenius acid base will be a Lewis acid base. Every Bronsted-Lowry acid base will be a Lewis acid base. Except in the long run, what we're simply saying is that this is a very specific definition. This is a very broad definition. Okay? That concludes 19-1.